All right, so we had some lecture 9 that we were kind of doing. So I'm going to start with that. And then I'll go on to the stuff for today. So we've been talking about particle charges and we talked about acid-base reactions. The other one was ion exchange. And this was the last slide that I had. And it's basically just a way of saying that ions can partition on and off of surfaces in a non-stoichiometric way, so they don't exactly follow equilibrium rules, but there's an equilibrium condition that applies that gives us an idea about the population of ions that stick on to a particle. So for clays in particular, this is an example of a clay. It's a really complicated structure. And this is the structure of the clay. It's a montmorillonite. The real montmorillonite that doesn't have any substitutions in it looks like this. And so when you look at this thing, you're like, oh my gosh, but it's written in a way that shows that this stuff here is in this site. So some iron 3 is substituted in, some magnesium is substituted in for aluminum. Iron 3 being +3 and aluminum being +3 gives us no charge imbalance. Magnesium being +2 gives us some charge imbalance. Then we've also got some aluminum substituting to our silicon site. And then there's some exchangeable ions on it as well, which are written off to the side. And these are things sticking on a surface that are able to stick on because of the charge imbalance, because of these substitutions. And this is just kind of the stoichiometry of that. And this is commonly what you'll see with clay minerals. They can have really complicated chemistry. So here's an example of a different clay, that series of clays, I should say, they're listed here on this side, where the original composition, taking them out of fresh water and then dumping them into salt water and seeing what happens. And so these are written as the kind of the mole fractions in the exchangeable fraction, sodium, magnesium, calcium, and potassium. You take it out of fresh water and stick it in the salt water, and you'll see some stuff change. And basically, I've highlighted, there's some little changes throughout, but the main changes are the sodium goes up and calcium goes down, as you would expect when you stick something into seawater. And that's just a measure of this exchangeable fraction. Now, the stuff that's interior to the clay that allowed it to have the exchange capability, that doesn't really swap out so easily. That's more like formation condition stuff. So, but that gives us this measure called CEC, which stands for cation exchange capacity. It's measured in milliequivalents, equivalent being a mole of charge, milliequivalent, so a milli, just like a milliliter being 1,000th of that, per 100 grams. I don't know who came up with this scale, but in any event, it's a scale. It tells us kaolinite has somewhere between 3 and 15 milliequivalents, 1,000th of a mole of charge in 100 grams of that clay. And that's considered low CEC. Vermiculite, the stuff they put in potting soil, high CEC, you can see it's like, yeah, maybe, 10 times as high. So that's a pretty big difference. And there's clays in between. And the names are not important, but what is important to recognize is that this cation exchange capacity largely comes from this kind of substitution. So some clays are more open and expanded and able to accept more substitution than others. And so that's what gives them different CECs. So the third kind of charge that we were talking about, how charge gets onto particles, is acid base, but in a Lewis acid, Lewis base sense. And this is the most complicated one. And I'm not going to kind of belabor it, but I want you to think about it. If a particle is positively charged and we have negatively charged stuff in solution, the particle can act like a Lewis acid surface, and Lewis bases in solution can come onto it, and vice versa. A negatively charged particle can do that. And what determines the sticking of stuff together is a function of the form of the particle and the form of the thing that's going to stick onto it, whether it's a Lewis base or a Lewis acid, as a function of pH. So it can get rather complicated, but this can have effects like organic acids can stick onto clay particles, and we'll see this is really important in riverine and estuarine systems for transport of materials downstream. The fate of phosphorus ions, which are used in solution by organisms for nutrients, to a lesser extent the amount of sulfate. So I have these plots here that are rather complicated, but really all they are Gerum plots, like we've been looking at, right? They got pH across the bottom, and they got percent across the top. And this is the example of aluminum hydroxide, right, which is gibbsite. Sitting there as a particle, and you can see it's got, as a function of pH, it can have no charge, it can have minus charge, it can have plus charge. And these are a bunch of different organic acids that can also change whether they are protonated or not as a function of pH. And so when we stick them together in solution, we find that we have the best association, how much stuff in percent is absorbed as a function of pH. And we see, or adsorbed, I should say. We can see that these chemicals absorb at different places. In general, once we get away from the pH equals pKa point for, in this case, the Lewis bases, which are sticking onto a Lewis acid, we don't have as much sticking, okay? And like I said, I don't want to dissect these in too much detail. I just want to kind of remind you that when these particle and solute interactions happen, they're pH dependent, and they depend on both things, the particle and the thing that's sticking to the surface. This is just another example. This is iron oxide or iron oxyhydroxide, like goethite. And then these are some other simple things that might act as Lewis bases in solution, like fluoride, phosphate, and sulfate. Again, Gerum plots. And again, you can see the same kind of thing, that for the most part, sulfate and fluoride will only stick to these iron particles at really low pH. But the interesting one here is phosphorus. And this is going to be important as we talk about nutrients and bioavailability of chemicals. You can see here that phosphorus, it has different forms, H3PO4, H2PO4 minus, H2PO4 minus, PO4 minus. But pretty much all those forms stick to the iron. So if we look at this curve here, we look at the sum of iron that's absorbed. We see that it remains high throughout. Maybe, you know, it's tapering if it comes down, but throughout most natural pH range, most phosphorus that's available sticks onto iron surfaces, which makes it harder for organisms to utilize that phosphorus as a nutrient. And again, that's another thing we'll see is kind of an important parameter in a lot of systems, whether we're talking about soils or groundwater or surface water, that are or aren't supporting biological activity is, well, how much iron is in it? In the 3+ form as particulates, because a lot of it makes the phosphorus difficult for organisms, you know, terrestrial and aquatic plants, to suck that stuff up. Now, the other thing that organic matter absorption on the surfaces, kind of like we have here in this case, is good at, is undergoing electron transfer reactions that help the breakdown of solid materials. That's kind of shown here. Here's an organic acid, carboxylic acid, and phenol sticking onto this particle surface. This is silicon oxygen tetrahedra. It's kind of shown in schematic form. And it can bind to this surface, and it helps to disaggregate it by allowing electron transfer to break bonds. And this is basically a plot showing you, well, for different kinds of organic acids that we stick in solution, how much do they help dissolving some material? This is dissolving of quartz. You can see these here in hours, right? 250 hours, and, you know, whatever that is, 12 days or something like that. So these are long periods of time anyway. But you can see here, water and acetate, which comes from acetic acid, which we talked about last time, they have the same rate. Salicylate a little bit more, oxalate a little more, but citrate, coming from citric acid, which is in citrus fruit, as among other things, really enhances the rate of dissolution, right? By something like a factor of, from maybe 2 up to 12, like a factor of 6. And it's from this kind of mechanism. So the final thing from last time that I wanted to mention is something about how does charge distribute around surfaces, right? So we already know there's 3 ways surfaces can get charged. We've got ions around them. This starts to matter, the orientation of charges, when our particles get really close together, right? So like, let's say we're talking about a very high particle content fluid stream, or we're talking about particles as solid materials in the subsurface that groundwater is flowing through. In both those cases, the distribution of charges around the surface affects how the exchange between stuff in solution and attached to surfaces progresses. So there's a couple of models. One of them is called a single layer model, where there's no fixed layer of ions, and one is called a double layer model. And the difference between them, and in both these examples, they've got a negatively charged particle, like a clay, with positively charged stuff sticking onto it. So in this case here, what you see is like the population of plus charged ions in solution relative to minus is such that you just attract more plus than more minus right to the surface. So if you were to somehow be able to measure distance from the surface of your particle in the water, you'd find more cations kind of parked near the surface and less anions, okay? So that happens, and these ions are pretty easy to exchange. In this kind of model, we get one layer of cations that sticks on like much more effectively. And then again, as we move further out into the solution, we see the same kind of drop off. So some situations, some ions and particles are single layer, some are double layer. The double layer models get more complicated. They all have these names. You don't have to worry about any of that stuff, only to know that either way, things that happen in a solution that can change either the particle surfaces or the ability of the solution to stabilize these kinds of ion clouds, we call them, around the particle surface, can change the way in which things that are associated with particle surfaces associate, either being associated or not associated with ultrafine particles that have particle charges on them. These charges can help solvate the particles, as we see when we talk about estuaries. And if we change something about the solution, like its pH or its salt content, that vastly changes this kind of behavior, that's going to change what happens on those particles. So this will become an important aspect when we start to talk about groundwater and when we talk about particles and estuaries, which are two places where there's a lot of solid relative to water, and the shape of these clouds really start to matter. And this basically just explains what I just said, so I'm not going to repeat it. And so that was the end of last time. And now I want to go on to the it's just a continuation topic. But so last time we talked about weathering and weathering minerals, especially clays and particles and substitution and interactions with solution. So today I want to talk about soil. Oh, sorry, I have the wrong textbook in here. Just ignore that. I'm going to delete it while we're here so that it's the same reading as from last time in chapter 6 and chapter 13. Apologize about that. So we're going to talk again about weathering, and I'll mention why clay minerals are important. But the distinction with soils relative to just weathering in general is that what makes a soil is it's got organic matter in it. So that's really the kind of definition, what I call the special sauce. So we're going to look at soils from the perspective of the weathering minerals as well as some of these solids. We'll look at some of the horizons that develop in soils, and we'll look at some examples from Hawaii. So these are some pictures of soils. I just kind of want to remind you that we interact with soil all the time, even if we don't realize we interact with soil. So we interact with it from the perspective of getting our food, from the perspective of aesthetics and conservation and what a watershed looks like. There's contamination, there's erosion, there's all sorts of things that happen with soil. So all these pictures are here from Hawaii, and you know, we're not immune to the problems that happen with soil or the processes in general, whether they're problems or not. So this is a table that kind of shows you what happens when you make soil. There's three things that always happen. You always have weathering, as we talked about last time. It's like, you gotta have weathering or you don't get soil. You gotta add organic matter. Again, it's not a soil if it doesn't have organic matter. And we got to make some kind of what we call structural units. These are the layers in the soil. They're given names. We'll talk about those names in a second. But these are a natural process of time and accumulation, right? And so you can have levels of maturation or maturity, you know, where you can have more or less of these things. And those give soils different names. They're names of soils that have something to do with how old they are. Now there's also all this other stuff that can happen, and these are all chemical and physical processes related to weathering. So you can leach out chemicals and you can acidify, you can alluviate clay, which means take little fine particles up in the water, up in the soil column and wash them down to lower in the soil column. You can podzolize, which means you're transporting dissolved organic carbon complexed iron and aluminum from upper horizons and then redeposit them lower down. And this is part of what helps develop these structural units, is this transport of chemicals down. We can take out silica, we can have reduction from oxidized states to reduced states as we get farther from the atmosphere. We can accumulate salts from water being added and then it evaporating out. We can make it more alkali, meaning accumulation of sodium, which comes along with salinization that helps neutralize some of the acid in the soil. And we can have erosion or deposition. Like I say, these sometimes happen, these always happen, but they're kind of a family of processes that are related together. And so soils, like I say, there are gradient in horizons and gradient in conditions from something that's very organic rich on the top to something on the bottom that's not organic rich. So the bottom layer of soil we sometimes call saprolite, and it is completely inorganic. Okay. And so the chemistry between the inorganic zone and the organic rich zone and the gradient between them can vary from place to place. But up here, you know, some of the things we've already talked about this semester are important because of the organic matter, complexation, chelation, acid-base reactions involving organic matter, dissolution, enhancement of solid particles by organic matter, supporting of biological activity as respirable organic carbon. All that stuff happens up here. It doesn't happen down here because we don't have the organic matter. So it's really kind of an important difference. And the difference in between these two things, and there are intervening layers, represent the development of these horizons as described here, and the accumulation of processes. And it takes time and you know, to develop these things. They don't happen overnight, and a thick soil horizon can represent hundreds of years, if not thousands of years of accumulation. But the one thing that's kind of important about this saprolite stuff is that if we're to look anywhere in the soil zone to say, well, we want to know something about the rock that this soil formed on, this is where we get that information from most straightforward. Because this is the least water soluble component of the weathering products of the breakdown of the parent rock, meaning the stuff the soil is sitting on, and it kind of accumulates down here. And so in this case, you can actually see some structure to it, which is probably related to the old rock. This is happens to be a zone where a saprolite layer is exposed at the surface because the rest of the soil has been eroded away. And so it happens to just be occurring here in a road cut that is visible. But like I say, it's most likely, if you go through an entire soil column, going down to the base to the saprolite is where we're going to find stuff that looks kind of like the rock it came from, the weathering minerals, the conditions, all that kind of stuff. And the higher up we go, the more likely we are to find other stuff, particles that came in on the wind, stuff that's been reworked and redeposited from elsewhere, organic matter, all that kind of stuff. And I just want to give you a little bit of context that, you know, soils are this kind of important interface point between the exogenic cycle of, you know, reservoirs that are the biosphere, the geosphere, the hydrosphere, and the atmosphere. They're like an interface zone. A lot of stuff happens there, and stuff that happens in one of those reservoirs can affect any of these others as they meet in this interface zone. And this is, for instance, the chemical inventory of three elements, calcium, magnesium, and potassium, in soils, in exchangeable ions, the things sitting on the clays, like we were just talking about, that are not, you know, part of the solid matrix, and living in the biome, right? The plants that are living on the soil. This is obviously just for a particular place. This is a place where beech trees were in experimental sort of farm forest setting for 150 years, right? So it's a stable environment. And what you can see here is that a significant quantity of these inorganic ions is up here in the biomass. The biomass needs that. The plants need that to support their growth. And I mean, even though these are really big numbers, that these blocks have been chopped down so they fit on the diagram, but even still, this is pretty big and this is pretty small, right? There aren't that many exchange sites on the clays in soils. And so if we do something to the soil to affect this, we affect this. So one of the things we can do to our soil is add acid accidentally. Oops, acid rain. Or we can add, in agriculture, we can add water that's got salts in it. Anything that displaces these ions, and the hydrogen ions that come from the atmosphere do displace other exchangeable cations on clays. They can reduce the soil's ability to support plant life because we're going into this little zone here and swapping out what's present. So it's kind of sensitive, even though there's a lot of the solid material present. It has to go through this transition zone of being attached to clays or exchangeable sites before it can be incorporated. So when we look at soils, there's basically two chemical components: inorganic materials and organic materials. And these are in three categories. There's the stuff that looks kind of like the original rock. So if we take the original rock and we start to weather it, some of the grains are going to be less susceptible to weather. That's why I gave you that Bowen's reaction series last time. So those grains pretty much always stay there, right? Even in very old soil, we can find some mineral grains. They're resistant to weathering, they don't break down, okay. But then we also get a lot of these, the alteration minerals, the ones that are the breakdown products of all the minerals that do break down. And then we have a third category, precipitation minerals, right? Everyone knows precipitation, that's just stuff that comes out of water. This can be stuff like calcium carbonate, it could be hydroxides of aluminum or iron. And what this implies is that the solubility conditions for those things change as we go up and down the soil column, right? So in some places they're soluble, in some places they're not. And these are particularly high in the intermediate zones of soils, what we call the B horizons, because this is where conditions change a lot, especially conditions of pH and conditions of how much organic matter is present. And then we got the organic constituents, okay? And these are derived from flora and fauna, especially microorganisms living in the soil, but with addition of leaf litter and those sorts of things. And the typical proportion is we got about 5% of this, about 95% of that. And you can find all sorts of variations. You can find soils with as much as 10 or 15% organic matter. They exist. And you can find soils with less. But this is just kind of an average. And so you can see soil is mostly this, the stuff we talked about last time, and a little bit of this. But it's just enough. That's why I call it the secret sauce to really change it. So of these three forms of solids, I want to look at them a little bit and talk about them and recognize that they can take different size and shape characteristics, which can affect how water flows through a soil. And that gives soil some names. And so this is basically, has everyone seen a ternary diagram before? Everyone's familiar with that? Okay. So this is a ternary diagram with three axes: percent clay, which is really fine particle, percent sand, which is coarse, and percent silt, which is in between. Okay. And so depending on the relative proportion of each one of these three things, you'll either have higher or lower porosity in your soil column and higher or lower permeability. Porosity is the volume percent of hole spaces in between solid grains, and permeability is their interconnectedness, how able they are to flow water or not. And so, for instance, soils that are based primarily on fine particles have a much more difficult time transmitting water through them than soils that are made of coarse material. And the weathering of those particles, this is just a repeat of a slide from last time. I just kind of want to remind you that the making of that inorganic material, there's physical things going on, there's chemical things going on, and there's biological things going on, and they all involve kind of water, right? There's water involved. Okay, and another kind of important thing which I'd like to emphasize, because when I learned geochemistry, we weren't thinking about organisms being everywhere and involved with everything, but they really are in the exogenic cycle. Microorganisms are very important in this process of breaking down of material, changing of chemical forms, complexation, chelation, localized variations in acid-base reactions, all that kind of stuff. And this is basically just showing you some of the places where bacteria sit associated with the roots of a plant that can affect the rate at which organic matter is broken down, the rate at which minerals are broken down, the rate at which myocordia affect the development of phosphorus-bearing nodules and roots, which help plants take and hold phosphorus. So, and like I said, it's a very schematic thing, but organisms in the soil are important for a healthy soil ecosystem. Okay, so now we're going to talk about these layers in soil, which I've mentioned. And I got a whole bunch of figures here that kind of say the same thing, and then I have a bunch of pictures, so I'm going to go through relatively quickly. But there's two key features I want you to remember. The first one is down here, we have soil horizons, which have names. You can get to really complicated names. If you take a class up in CTAR and soils class, you're going to learn a lot more detail than you learn here in the next 10 minutes. But soils in general can be divided into an A, a B, and a C horizon. The A horizon, sometimes called the topsoil, is the most organic rich and the least like the rock that it came from. The C horizon, which before I mentioned is called saprolite, that's the name we refer to it. It's the most like the rock. And in between, we have the B horizon, which is sometimes called the zone of accumulation. Because water's percolating down through here, conditions are changing. And as the conditions change, stuff that was up here that was dissolved with the water precipitates out, gives this zone a particular kind of color and character because of the precipitation of things like iron oxides and aluminum oxides and calcium. So there's that. There's also, well, how much water is in our soils, okay? And this is going to be important when we talk about groundwater again, but we can have places where we have an open core network of spaces in our soil. Our grains may be wetted. That just means if there's a little bit of water present, it's usually stuck onto the surfaces. But these spaces are open, and then sometimes they can exchange with the atmosphere. We call that vagose or unsaturated, okay? Because it's not full of water in all the little holes. Once we get down below a certain depth, the water, those holes become filled with water, the water table, as you will. That's what we call the saturated zone. And from the perspective of soil chemistry, if this thing is stable or if this horizon between the two migrates a lot, it's going to affect the composition of the soil. It usually happens down here in the B zone. Sometimes it happens deeper. But once we get filled with water, we tend to not be able to exchange with the atmosphere anymore. And so if you remember the redox example I gave you of a flooded soil that was flooded all the way to the surface, and we watched the soil water change redox really quickly, because the ability to exchange oxygen with the atmosphere goes away. And so it can affect the local redox state around the particles. And as you can infer from, this last, this slide here, that also affects what's living within the soil, right? Some soil microbes don't like the change in PE conditions. Some of them don't mind. So this just kind of summarizes A zone, the top, least like the rock, most organic rich. The C zone, most like the rock that it came from, and the B zone is the place, the zone of accumulation. There's a couple of other kind of more detailed graphics. This one's showing you the relationship between the horizons and land plants and animals living under the ground surface, like ants and gophers. Pretty much, these things are restricted to relatively high in the soil. You can see how some very large tree roots can go down from the A into the B horizon. They don't make it down into the saprolite C zone, which in this graphic is shown as a transition between saprolite into unweathered bedrock. And notably, you can also see subhorizons in the A. So the A layer can often be divided up into a bunch of different layers. And again, we're mostly not going to worry about here, but here's 3 common layers that are found within the A horizon. So A, subhorizon 0, subhorizon A, and subhorizon E have different amounts of organic matter, and the resistant mineral grains, which I've mentioned before, they kind of accumulate at the base of the A zone, which organic matter is up at the top. And again, it's not super important, other than to recognize that when a natural soil, these things develop over time, centuries, if not millennia. In agricultural soils, we're constantly disrupting that, right? We're digging it up and trying making a homogeneous column that we add a bunch of amendments to so that it can support plant growth at 1 or 2 orders of magnitude higher than natural. Agricultural soils can be really complicated things, and we don't focus on them in this class. We talk about them a lot in the environmental geochem class, which is in the spring semester. But all of the processes I've already talked about so far, like the storage of ions and the support of biological productivity on the surface and the organic matter and the pH and nutrients and contaminants, which also manage to get their way into agricultural soils due to agricultural practices, how those things transform and accumulate or redistribute into the water table underneath are greatly affected by human activities. Just so you know, I mean, they're a very sensitive zone, and they sit at this important interface. So this is one of the things that happens in the zone of accumulation, which is easy to track, which is the formation of caliche, which is a type of calcium carbonate that precipitates out of soil water when either the amount of water that's present goes down, like let's say we have a place that goes between wet and dry, and when it starts to dry out, we start to precipitate, or it can precipitate as a function of changes in pH as we go down through the soil column. But it's a solubility zone in the soil where as we go from top to bottom, all of a sudden we find calcium carbonate present, which means it's no longer soluble. If we find calcium carbonate as a solid making caliche horizons, I'll show you a picture in a second, then calcium carbonate is not as soluble. And you can see here that one way, this is the depth down within a soil in inches, and this is rainfall in centimeters. I don't know why they mixed, metric and imperial systems together in this plot, but it was the only plot like this I could find, and it's from the 30s, so go figure. But what you see is that the more the rain in a certain place, right? So 100 centimeters, about 25 inches of rain, the deeper we find this horizon. We're basically pushing it down further and further into the soil, but it pretty much is commonly found in most places. Okay, and what it really tells us is that somewhere deep down in the soil, in a place where it rains a lot, or somewhere up near the surface in a place where it doesn't rain a lot, we're going to find these precipitates of calcium carbonate, and they're telling us that the pH is changing. Okay, so we make calcium carbonate from having calcium ions and having bicarbonate or carbonate anions. A lot of that carbonate actually comes from respiration of organic, right? Just like we breathe out CO2, soil microbes produce bicarbonate. So you can have a bunch of calcium in the water, and all of a sudden you can have extra biological activity, and they can start to produce a lot of bicarbonate ions. And as we migrate down in the soil, we'll see that our pH starts to increase as we go down. And so when it increases to a certain point, the bicarb to carbonate ratio gets to the condition where we can start to make some calcium carbonate. So it's really a combination of effects. And it's not so much just the water affecting the solubility. What it really is that the water is affecting the biological productivity. Okay, wetter places tend to have more biological productivity on the soil and in the soil. Biological productivity produces organic acids, and organic acids lower the pH, and low pH is unfavorable for calcium carbonate precipitation. So life in this instance is really kind of affecting pH through organic acids. So this is an example of what a caliche horizon looks like. See this little band here through the soil? It's oftentimes not quite so perfect, but you can see this is a really arid environment, low rain. This is, these are 10 centimeter blocks, so that's like 30 centimeters down into the soil, which is about 10 inches or so. And this is common. We find this really commonly here in Hawaii, especially go into the leeward areas or some of the islands in the rain shadow like Lanai. And in fact, in some early geological reports, people confused this stuff as being related to kind of sea level being at that stage in the past, and kind of precipitation of marine carbonate, which it isn't. It's an inorganic carbonate that comes terrestrial. So I have a bunch of other pictures of soils. I'm just going to kind of quickly go through them. Some of these come from a guy's LinkedIn. There's like a soil guy that has a bunch of really great pictures of soils. But I just kind of want you to see, this is what the top zone looks like, the A horizon. This is more A horizon. This is the B horizon. See how bright orange it is? This is the zone of accumulation. That's what the B horizon is often called, where stuff is washing out. There's also some alluviation of clays. So we get a finer particle matrix in here, and we get these color changes because of pH and organic matter content changes, which allow things that were soluble in the water, as they percolate down, to become insoluble in the water and precipitate out and kind of change the color. And this is a particularly dramatic example. This is another soil horizon. Okay, this is from the USDA website. The gradients are a little bit less strong, right? There, but you can still see the organic rich layers have a deep, dark brownish color from the organic matter. Then we go into this kind of more orangish layer, and then we get down into this kind of zone of accumulation. Another soil where you'd be hard pressed to find the horizon, right? There's a variation in texture, right? You see it's kind of coarse, and you see there's a little bit rubberier up here, a little bit less. But this is a common condition in tropical areas where there's a lot of rainfall. It's very oxidized conditions. We get very thick soil horizons, and we have very little organic matter. So mostly we just get the really resistant minerals that we talked about last time, the quartz and iron oxides, along with kaolinite, clay, or kaolin when it's in a rock deposit. And in this case, there isn't much of a horizon, set of horizons here. Here's another soil from a temperate region where, again, we can see the horizons. And this is a very young soil. Okay, that's what an ensisol is. It's got a lot of rock in it, a lot of rocky debris. We can see our organic layer. We can see our zone of accumulation. We can get down to our satellite. This is the rock upon which it's based. This one happens to be based on a sedimentary rock deposit, which makes it a little bit more complicated to identify what comes from where, because the sediment itself is an accumulation of materials. But we can see that the soil horizons themselves are developing into the parent material in a way that still preserves a lot of parent material bits relatively high up. And this is characteristic of a soil that hasn't been developing for very long. This is an example of a soil built on sandy materials. Okay, so again, we can see the transition between the topsoil down. The main transition here is yes, organic matter and not organic matter. Kind of a complicated interface between these two things. That complicated interface can be affected by what we call bioturbation, which is when we have ground-dwelling organisms that are moving around grains and so forth. You can also see where the roots are and so forth. And so again, and this is in an agricultural setting. There's another place where it's kind of hard to see the soil horizons, but you can kind of tell the change in color. More organic rich, less organic rich, more clayey, more iron oxide precipitation going on there. Here's a soil in a very, very wet environment. Again, not very much in the way of horizons. There's a little bit going on down here, but it's very organic rich. You can see the roots going all the way down. And the combination of cool temperature, so this is a cold climate environment, and very, very high organic matter deposition for a long period of time, like think like peat bog or something like that, allows us to get to these kind of relatively acidic, organic rich, thick top zone layers that basically inhibit the kind of development of the lower horizons. They may be down there, way down below. But this kind of tour is just meant to show you that, well, there's a wide variety in actual soils. This is another example of a very organic rich peaty soil, which can have up to 25% organic matter. They stay wet throughout the year. And you see how dark they look. We're not going to find the B zone in that soil. And here's another example of a very arid soil, where again, it's kind of hard to see the horizons. We don't see much development of organic matter. We see some roots down in here, and then we transition into this kind of coarse, kind of more blocky or rubbly zone, where we're starting to see a little bit of color change, precipitation minerals, perhaps along preferred flow paths, such as along here as water percolates down. But this is a low organic matter soil. And here's just a few from Hawaii, just to show you some examples. This comes from the CTAR website. So, something in a relatively arid environment, very oxidized, very iron rich. That's where the orange color comes from. Something very wet and organic-y, something kind of in between. And again, the horizons are not well developed in these upper parts of the soil column. So this is something I don't want you to memorize. I just make yourself a note that it exists. There are ways to classify soils on the basis of how long have they been around and how well developed they are. And there's a name progression that starts from something that's very young to something that's very old and things in between. There are also naming conventions that have something to do with the parent rock that they came from. Right? Are they based on kind of volcanic rocks? Are they based with high in iron or metamorphic rocks or rocks that are high in calcium and aluminum? And I don't want you to memorize any of that stuff. I just want you to know that time is one of the factors that contributes to soil development and soil character. The other two are the climate, right? Is it wet? Is it dry? Is it hot? Is it cold? All the things that I was pointing out on those soil horizons, those matter. And what is the protolith, which means what is the bedrock? All three of those things matter and what you find in the soil, and people give them different names, and we're not going to worry about the names, but I just want you to know that the names exist. Okay, and this is just a table with some of the names of the soils, young soils, more well-developed soils, and what defines them. And oxasols, reddish soils of low latitudes are common here, for instance. Where they derive from. And this is the relationship between some of those names and the other two parameters besides time, which are climate, wet, dry, hot, cold. Okay. And as you can imagine, just thinking about it in your own mind, most places that are dry and cold, very limited plant life. Hot and dry are also pretty limited. Wet and hot, lots of plant growth. Just think about like here, cold and wet, depends on how cold, but can also have a lot of plant life. So it's kind of an organic matter contrast as we go this way. One of the things organic matter always means, hopefully I've hammered this into you enough, is increase in acidity from organic acids, as well as the ability to complex and chelate. So that increases as we go across. And that's one of the things that contributes to soil productivity. And these are just some of the soil orders in Hawaii, what the names and the examples of what they look like. And you can look through this stuff in the notes at your leisure if you're interested. And I've given you, you can read all about this on the CTAR website. I've just given you an example. This is a map of the island of Lanai, which has a spur of mountains over here called Lanai Hale. Maui's over there. And this is the former caldera. It was used as a pineapple plantation for about a century until about 15, 20 years ago. And you see the distribution of the soils. So we see these very oxidized and low organic rich soils kind of accumulating here in the caldera. We see soils that are younger and more more well developed, associated with the places where it rains a lot. So this is pretty much the only part of the island that's got kind of verdant plant growth, and the rest of it's pretty dry and deserty. And you can find these similar patterns on the various islands. Where do we find the weathered soil? Where do we find the young soil? Where do we find the thick soil? Et cetera, et cetera. It'll be a combination of the climate factors plus human predation, right? In this case, this was agriculture and not agriculture, and so that affects what we find. Okay, so now I have a couple of slides that look at the chemical transformations in the saprolite layer as it's developing. And I realize they're a little bit complicated, and so I'm going to try to walk you through them and ask questions if you have questions about them. But what we're really looking at is as soils, this is not one soil, but a variety of soils with different characteristics progress, we see a change in the chemistry and the mineralogy that supports it. So these two things link together. And I've colored in each of these lines to try and help show you that. But what we see across the bottom is the percent of aluminum increasing. So one of the things that we do in the geosciences is when we're measuring the composition of rocks or sediments or soils or anything like that, because of going back into the olden days when these measurements were usually made by first sort of a chemical disaggregation of the rock and separation into different piles of powders that were oxides, we measure things in percent oxide. That doesn't mean to say that this soil is 26% aluminum oxide. It isn't. This is the amount of aluminum in the soil expressed as an oxide. Nowadays, we make these measurements with the instruments that allow us to not disaggregate the material. But by convention and tradition, we still report most concentrations in most solid materials. So whether we're talking about a volcanic rock or soil out here, in weight percent oxide, right? So like, what's the weight percent oxide of magnesium? What's the weight percent oxide of iron? If you think back to that problem you guys did on the first homework, those were weight percents. Those exact, the rock is made of those things, but not the exact way that they're being expressed, if that makes sense. They're being expressed as the percent pure oxide. Okay, and so when you look at this diagram, you see basically, as this increases, think about it, aluminum is one of our two most resistant to weathering elements. When we looked at that flow chart of how stuff dissolves in water as we go through a weathering process, aluminum and silicon tend to accumulate. So this going up is the progression of weathering. It's just a track of the progression of weathering from a little to a lot. Okay, and this is changes that happen while that happens. So here we're looking at minerals. Well, what do we see? Plagioclase breaks down pretty early and then it's low. The more we weather, the more plagioclase we break down. Quartz increases in concentration, okay? Because it's a resistant mineral until we get to really extreme amounts of weathering where we can start to dissolve it. Potassium feldspar, again, a little bit more resistant. It's lower down on the Bowen's reaction series and plagioclase. It increases to a point and then it breaks down. Iron oxides increase. Mica grains decrease, okay? And when we look at the chemicals associated with them in the solids, what we see is that some elements, like the sodium and the sodium and calcium, they go down really fast. They get leached out of the soil. Some of them sit on the exchangeable cation sites, but mostly they're going through in the through-flowing water. So weathering removes these things, okay? Titanium builds up because it's one of these insoluble elements. It's part of the elements of the resistates. And so we see its concentration building up. We also see iron building up, okay? So this means that iron is in its +3 form, which is insoluble, not its +2 form. And so that implies that it's an oxidized condition. We see silicon going down, we see potassium going down. It goes down much more slowly than sodium and calcium. It's like, well, why is that? Well, because the potassium is mostly held in these kinds of minerals, potassium feldspar and in micas, which break down more slowly in those conditions in plagioclase feldspar. So the potassium hangs around longer. So you might say, well, maybe that's one of the reasons why, you know, life evolved in such a way that it uses potassium much more so as a micronutrient plants than it does sodium or calcium. Perhaps. I'm not saying that's what it is, but a combination of factors involved. But the fact that potassium sticks around during weathering processes more in soils probably contributes. Okay, so the gist of it is that some elements go down, some elements go up, some of them go down or up quickly, some of them go down or up more slowly. This is all happening during the progression of soil formation, which can be measured, as a function of this parameter and this parameter, right? So there's all these things that are going on at once. And that's what makes all those soil horizon pictures I showed you look so different. Every place is a little bit different. But there's generalized processes that go on, okay? And this just explains, I'm not gonna read through it, but this explains each one of those things that we find in the soil horizon. So that's the solvent. So now I want to segue over to talking about, well, what about the water? The water that's down there in the soil. What's it got? And what's it doing? And it's basically what's in the water is a measure of, well, how soluble is stuff? And that's why we've been talking about solubility. Stuff that's really soluble is going to be in the water. Stuff that's really insoluble is not going to be in the water. Okay. And so there's kind of two processes. There's the breakdown of that bedrock down at the base, right? And some stuff's going to be soluble, and some stuff's not, by the kind of stuff we've already talked about. And that's going to help set what are our weathering minerals? What are they? What are they made of? Do we have clays with high CEC or low CEC, etc. And then there's, well, what about when we add in some organic, some dissolved and particular organic carbon? And we're going to unfurl the chart just to remind you of which elements we're talking about here. These ones in the middle, I think a little bit difficult to look at. I guess good enough. See how iron, and I pointed to these before, but iron, which is this really important chemical in soil, part of what gives it that color and everything else, its solubility really changes as a function of the amount of organic matter. Plus all the things that are around it, cobalt and nickel and copper, et cetera, et cetera. So we can see that those elements are going to vary a lot in the soil column. We go from top to bottom because of the presence or absence of organic carbon. Whereas the cations, the sodium, the calcium, potassium, magnesium, this stuff doesn't really care about this. Okay. And so we can look at soil water and we can say, all right, first off, what's there? And second off, is it free ion or is it complex by organic carbon? And that's going to tell us something important, because the stuff that's complex by organic carbon is likely to change as we go down through the soil horizon as a function of there not being much carbon when we get down low. And this is the gist of the zone of accumulation. That B horizon, where we start to see the precipitation minerals, is basically because as we go down to the soil, we lose our organic carbon, okay? And then we lose the ability to chelate those things, and elements like iron, which had been chelated, come out and make us this kind of brownish zones where it precipitates out of solution. So this is an otherwise kind of complicated plot. Got a bunch of elements. It's a 3D plot. It's got this axis coming out, which is the height of the bar, which is concentration. It's got the soil horizons. It's divided up to A into a organic rich topsoil and a not organic rich lower horizon. It's got the B zone, zone of accumulation, the C zone, the saprolite. And then the bars are stippled is the total concentration, and the solid fraction of the bar is the amount that's complex. Okay. And so you can basically see two kinds of behaviors on this diagram. You see elements that go down, like copper, right? It's high here, it drops off. Chromium, high and drops off. Zinc, high, drops off. Magnesium doesn't change all that much, but it's a little bit higher and it drops off. Then we also see elements that have the opposite behavior. Iron, low and then increasing. Okay. Aluminum, low and then increasing. And so this variation, and now if you look at the proportion of 100% complex, 100% complex, 50-50. About 50% complex, all complex, no complex. All these elements over here, there's no complexation. So this is basically just solubility in an inorganic perspective, primarily because of pH. pH effects on aluminum hydroxide solubility, pH effects on calcium carbonate solubility, for instance. Magnesium partitions into the calcium carbonate phase. So again, its solubility is, those are pH driven. Whereas these guys that have a significant fraction of bar complexation, it's telling us how much of that stuff is present as a function of how much organic matter is present. And they are being carried by the organic matter and associated with the organic matter, at least sort of up to half of the time in some of these cases or more. And so they're inextricably linked. Okay, so we talked about the solid grains, we talked about the water, now let's talk about the organic matter in the soils a little bit. So, as I mentioned before, it's about 5%. We can get up to 25% or so, 25%. But this small amount in most typical soils does a lot of different things except the availability of nutrients. It supports soil biota, it binds organic contaminants, it helps determine soil pH through dissolved organic carbon, and it mediates mineral dissolution through dissolved organic carbon. These are all things that we've been talking about already last time and prior. This is an example of some of the common small organic acids. I've mentioned some of these before. We looked at citric acid before, right? That's what oxalate looks like. And how these kinds of chemicals can be involved in the dissolution of solid mineral grains. It's a combination of binding to surfaces, stabilizing them through Lewis acid, Lewis base interactions, and breaking the bonds out of the matrix. And this can contribute to localized oxidation and reduction. This is just an example showing you how bacteria, which produce and excrete these things in soils, can help enhance the rate at which weathering is happening. This is an image showing you the locus of bacteria that are conducting the breakdown of the rock particles here. And so when we talk about these processes, even though they sound like chemical processes, and they are, we want to remember that they're mediated by organisms. And so the presence of those organisms is playing a big role in how things happen, okay? This is just a reminder of that plot. I showed it to you a little bit earlier, but I'm just showing it to you again, that in essence, some of these organic materials are better at dissolving solid grains than others. And depending on, it will change depending on what it is that we're dissolving. But life producing organic materials then is enhancing the rate of weathering is a really common feature in soil development. So this is a table telling you the different kinds of organic matter we find in soil. There's a huge range. This is just a breakdown into a few of them. Now we've talked about the humus and how it divides up into humic substances, humic acids, folic acids as a function of pH. That's what that is. We also have other kinds of specific things, fats. These are primarily hydrocarbons, fats, resins, waxes, saccharides, which is a fancy way of talking about cellulose and starches. Then we also have these categories here: chemicals that contain nitrogen and chemicals that contain phosphorus. And the reason they're called out is because plant life needs those things. And there are microorganisms in the soil that are breaking down the organic matter and liberating nitrogen and phosphorus so that then they become bioavailable for plants to take up. And so this is kind of like storing chemicals in the bank. If you have a lot of organic matter in your soil, in a highly productive soil, and you've got organisms that are transforming that and liberating nitrogen and phosphorus, becomes available to plants. And so this is part of a healthy soil, is having these chemicals present, which are largely produced by plants that lived on the soil before. Okay, so related to all of this, especially organic matter, is the pH. So this is from a soils textbook showing you pH again, and we've looked at pH before from the perspective of rainwater, CO2 solubility, and all that kind of stuff. And remember, we kind of go from around here, the lower endpoint of CO2 in rainwater and river water, and we get to the ocean, we're up here at pHs like this. Those are broad generalizations. You can find localized zones on the planet where we have a bigger range in pH. Just like our soils here in Hawaii tend to mostly be less than 4 in the soil, right? And that's because of stuff that happens in the soil in addition to what's happening up in the atmosphere and the rainwater. And you can see here that in general, the wetter the environment, the more acidic. What's that wet coming from? I mean, what's that acidity coming from? Organic acids. So those organic acids are coming from the biological activity living on and in the soil, and that is promoted by humid environments. Whereas dry environments tend to be more arid. I should say more arid. The dry environments are obviously arid, but they tend to be higher in pH in general. So we have these kind of variations, and human activities can enhance that. So here's all the stuff that can affect pH in the soil. Okay, and it's a big table again, but it's a combination of addition of acids and acid-forming chemicals from the atmosphere, removal of base cations, some oxidation processes change pH, microbial production of organic acids, increase of soil organic matter content, loss of ammonia. This is pretty rare, but ammonia is a base, and so under some conditions, this will happen. It's mostly very cold, temperate region, wet forests, and then fertilization with ammonium salts, which means something artificially done by humans. These can all increase acidity. Things that can increase alkalinity, which is the opposite of acidity, are the addition of atmospheric particles, like carbonates and weathered silicates. Some reduction processes can lower the pH, raise the pH. Some weathering, obviously, hydrolysis of some exchangeable ions. These things can increase basicity, but there's more things in this list than in this list, and in most soils, we tend to find them getting more acid over time. So if you think back, I said, oh, well, time is one of the things that sets the soil odors. This is one of the ways it does it. Primarily through combination of exposure to the atmosphere and the development of organic matter in the soil. Once we get into non-natural situations, human perturbed situations like acid rain or agricultural processes, pretty much everything we do favors this over this. So we enhance this rate, but it's a natural thing that happens anyway. Soils do acidify over time. It's just, like I said, human activities can change the rate of acidification of something that might have happened naturally over 1,000 years. We can do in a couple of decades, and then make that soil unusable for plant growth. And so you say, oh, how does soil affect things? Soil on pH affects a lot of stuff. One of them is how available various ions are as a function of pH, right? And so pH going from low to high will affect how protonated our organic acids are in the soil water, which will affect how available various chemicals are that are complex by those organic acids. So all these chemicals up here in the middle of the chart, which are sparingly soluble, but become enhanced in the presence of organic matter, may not be enhanced throughout the entire pH range because their binding characteristics for organic matter depend on pH. So this is an example showing you pH between 5 and 7, fairly narrow range. And then these are log scale. It's sort of a complicated plugin, but these are log scale plots kind of showing you that molybdenum goes way up as a function of pH changing. All these other ions go down, some not by very much. Lead, mostly in here as a contaminant, something that we worry about. Its binding characteristics don't really change as a function of pH, but all these other elements do. Cadmium, again, in there as a contaminant. These are micronutrients. Molybdenum is an important nutrient element. It forms part of the electron transfer center of proteins called nitrogenases, which many plants use to help oxidize nitrogen that it takes in from the atmosphere and make it into a biologically relevant form that it can incorporate, into plant tissues. And so the ability of plants to do that depends on their ability to take molybdenum out of the soil and incorporate it into the plant to build into these nitrogenases, and that changes as a function of pH. And of course, this is a snapshot between a particular location in a particular soil, but you kind of get the point, the gist of it. So the last thing I want to talk about are nutrients in general. Okay, I probably won't get through this whole topic. I don't want to overwhelm you, but when we think about nutrients, in this perspective, we're talking about the stuff in a soil that helps support plant life. And later, coming up in a coming week, we're going to talk about nutrients again in aquatic ecosystems from the perspective of, okay, they're supporting photosynthesizing organisms living in the water, algae. So we can break our nutrients into several categories. There's nitrogen and phosphorus. These are called macronutrients because plants need a lot of them. So we find high concentrations in plants. There are also some major cations, potassium, magnesium, calcium. These are also essential. If we had a soil that had none of those things in them, even if we have tons of this, plants are not going to grow, or many of them won't grow because they are critical. Then there's some anions that are important, mostly sulfur and fluoride. Then are what we call the micronutrients, micro because we need like a little bit of them. We don't need much, and actually too much can be toxic, but we need some. And again, if it's not present, it can limit the biological activity on the soil. Okay, so there's a relationship between carbon, nitrogen, and phosphorus. This is a molar ratio for terrestrial plants. And this is like, okay, take every terrestrial plant on the planet, stick in a blender and get an average, right? It's a very coarse average. But it says that for every 1,200 atoms of carbon, there'll be 35 atoms of nitrogen and 2 atoms of phosphorus. And I mentioned to you earlier in the semester what aquatic photosynthesis looks like. It has something called a Redfield ratio. We'll come back to this again. But that ratio, and this is again, take like aquatic photosynthesizing microorganisms, phytoplankton in the oceans, and aquatic algae in fresh water. Stick them in a blender, blend up, you get 106, 16 to 1. So you can see here that this ratio, 16 to 1, 17, or whatever it is, 17 and a half to 1, they're pretty similar. The nitrogen and phosphorus demands are pretty similar throughout the plant kingdom because there are metabolic phenomena that go on that use similar chemicals and processes. The difference between the relative amount of carbon in these two things is all the infrastructure that land plants need, right? They need bark, they need to be able to stand up tall, whereas these guys just float around in the water. They don't need nearly as much carbon to build up tissue mass, okay? But in general, the production of biological material with these average ratios by plants in terrestrial and aquatic ecosystems is never limited by the availability of carbon. There's pretty much always enough carbon around until we go down deep into the earth, where we're not doing photosynthesis anymore. But at the surface of the earth, where we're supporting photosynthesis, we've got plenty of carbon because we've got it in our atmosphere. And so what limits biological productivity is often the nitrogen or the phosphorus. And if it's not those, then it could be being limited by one of these other three things. There's a lot of stuff that can have an effect on the biological activity in an ecosystem. This is the Redfield ratio I just mentioned. And the only other thing I would like to point out about this relationship is that things change in a predictable pattern, right? Like nitrogen and phosphorus are consumed together when we take these inorganic constituents and we make algal protoplankton. That's just respiration going this way. And photosynthesis going that way. Respiration is like what we do. We take oxygen and we decompose this stuff and spit it back out in this form. And again, this is schematic. But the ratios, the way in which these things vary, this varies in a ratio of 16 to 1 in aquatic ecosystems or 17 and a half to 1 in terrestrial ecosystems. On average, it's an average. When we do photosynthesis, we consume a little hydrogen ions. When we do respiration, we produce a little bit of hydrogen ions, et cetera. You can calculate just from the stoichiometric coefficients that, like, for instance, if we see oxygen going down because of respiration, we expect these things to go up in the environment in their stoichiometric proportion. And we'll return to that later. So I just put it there to emphasize the role of nutrients. So this is a table showing you kind of, for an average plant, terrestrial plant, Here's the kind of dry weight percent of carbon, oxygen, hydrogen. Then the macronutrients, and here the potassium and the calcium and the magnesium and sulfur. Some of the categories I separated out on a prior slide are all lumped together, but mostly you see the nitrogen and the phosphorus. The concentrations are not that high in the plants, right? They're fractions of a weight percent except for nitrogen, but they're essential. And then these micronutrients, they can be present at very, very low concentrations. Again, they're still important, but they're at low concentrations. And so I think I will stop there to leave the last few slides for next time. The last thing I kind of want you to think about as you're thinking over the weekend is how everything we've already talked about now fits into an ecosystem, right? We got layers in our soil, we got plants living on the soil, we got rain coming in, we got dust coming in, we got the accumulation of organic matter, we got leaf litter falling. All these processes are going on and giving us the development of those soil horizons and the compositions and the layering and all that kind of stuff. And this is really important, we're going to talk about groundwater coming up. Water that flows through this system and carries with it the stuff that doesn't want to stay behind. This is the source of a lot of the composition in a lot of groundwater. So whether we're studying groundwater or whether we're studying soils or whether we're studying terrestrial ecosystems, what happens in this zone matters a lot. There's a lot of accumulated processes to happen. All right, any questions?
Not yet.